Characteristics of a controllable switch. Switches are used to control electrical and electronic devices and appliances. A switch can either be in off state or on state. When it is off, the electrical or electronic devices draw no power from the source. When it is on, the electrical appliances or devices draw some power from the source. So in off condition, the load is drawing no current from the source as the switch is open, and the source voltage appears across this switch. And in on condition, the switch is closed, the circuit is complete, and a current flows from the source to the load. In this condition, there will be no voltage drop across the switch. Apart from this off and on state of a switch, we can have forward and reverse mode of these switches. In off condition, the switch is open, so there will be no current flowing through this. In on condition, the switch will be closed, there will be a current flowing through the switch. When a switch is set to be forward, it means that the anode terminal is at higher potential than the cathode terminal. And when it is set to be reverse, the anode is at lower potential than the cathode. So with this combination of off, on, forward and reverse, we have various switch configurations: forward blocking mode, forward conduction mode, reverse blocking mode, reverse conduction mode. Whenever we describe switches in these configurations, we also describe the IV characteristics or VI characteristics of the switches along with their operation. The first mode is forward blocking mode. As the name suggests, forward. Hence, the anode will be at higher potential than the cathode. This will happen when the source is at higher potential than the load. And since the name suggests blocking, this means the switch will be open. Hence, no current will flow from the source to the load, and the entire source voltage will drop across this switch. The VI characteristics of this blocking mode, forward blocking mode, is shown in the right figure. As we can see, there is no current, only a forward voltage that is blocked by this switch. We are calling this voltage as forward voltage because the anode is at higher potential. Next mode is forward conduction mode. In this mode, anode is at higher potential than the cathode and the switch is closed. Due to this, load draws certain current from the source and there will be no voltage drop across this switch. We can see the VI characteristics. There is only forward current, there is no voltage in the forward or reverse direction and no current in the reverse direction. The next mode is reverse blocking mode. As the name suggests, reverse, the anode is at lower potential than the cathode. This will happen when the load voltage becomes higher than the source voltage. Since the switch is open in this mode, there will be no current flowing through the switch. And the entire load voltage, in this case the load voltage, will appear across the switch. Since the switch is in reverse mode, we can show the VI characteristics as shown in the figure to the right. There will be a reverse voltage that is blocked by this switch. The last mode is reverse conduction mode. In this case also, the load is at higher potential than the source, so the cathode is at higher potential than the anode. But the switch is closed, hence current will flow. But this time the current will flow from the load to the source. And again, since the switch is closed, there will be no voltage drop across this switch. And we can see the VI characteristics on the right. There is a reverse current flowing through the switch. So there are various characteristics of an ideal controllable switch. We call a switch a controllable when we can control that switch. We can control the turn on and turn off of that switch using electrical signals or electronic pulses. Now, when we say ideal controllable switches, then these switches must have certain characteristics. The first one is that an ideal controllable switch blocks arbitrarily large forward and reverse voltages. It tends to infinite in case of an ideal switch. And when they block certain voltage either in the forward or reverse direction, we say the switch is off and there must be no current flowing through the switch. Second characteristic is that they conduct large currents when they are on. So if a switch is on, they are able to conduct a very high current or large current. Ideally speaking, they can conduct infinite amount of current. And in this condition, there should be no voltage drop across the switch. Now, if the switch is turned on from off position or vice versa, this triggering, when this state are changing from on to off or off to on, we call this as triggering. So for an ideal controllable switch, this triggering should be instantaneous. And this triggering should draw very small amount of power from the control source. So these are the characteristics of an ideal switch, but we can see that these are not followed by a practical switch. So there will be certain current flowing through the switch even though that switch is off. There will be a certain voltage drop across the switch even though that switch is on, and there will be certain delay in transition from on to off state and vice versa, and a considerable amount of power will be drawn from the control source. This is explained in this switching characteristics. Switching characteristics are drawn when a switch makes a transition from on to off state or off to on state. So to turn on the switch, we have this control signal, which is nothing but a positive gate pulse. And to turn off that switch, we provide negative gate pulse. We can see the voltage across the switch drawn by this red line color and the current flowing through the switch in this blue line color. So as long as the control signal is negative pulse is there, the switch will be off, and hence the entire source voltage or the load voltage will drop across the switch. At this instant of time, we apply a positive gate pulse, but we can see the voltage does not become zero instantaneously. It falls gradually. Similarly, the current does not rise to its maximum value instantaneously, it rises gradually. So there is a delay, which is unlike ideal characteristics. So the time in which the current rises from its zero value to the 10% of its maximum value, it is known as the delay time. In delay time, the voltage drops from its maximum value to the 90% of its maximum value. Then we can see the current further increases. The increase in current from 10% of its maximum value to the 90% of its maximum value takes during the rise time. So we denote this time as rise time. So we can see, though the gate pulse has been applied in this time, the current through the switch establishes after this time only. So this entire delay is known as the on time or the time to on the device. This T on is then the sum of delay time and rise time. And we can see there is certain loss across the switch, and this is known as switching loss because it is appearing only when the switches are making a transition from off to on state or on to off state. Now as long as the switch is desired to be on, we keep the control signal as it is. So the control signal is positive here and the current through the switch is maintained. Again, we said that an ideal switch must have zero voltage drop when it is conducting current, but in this case we can see there is a very small or negligible voltage drop across the switch. Due to this negligible voltage drop, we can see a very small conduction loss, but this conduction loss is almost negligible as compared to the switching losses. Now again, if the switch is desired to be turned off, we provide negative pulse to the switch. That is, we try to apply a reverse bias across the switch. Again, we can see the current and the voltage, they do not change their value instantaneously. There is a delay. So there are two times, storage time and fall time. During the storage time, the voltage rises from its zero value or this minimum value to 10% of the maximum value. Simultaneously, the current falls from its maximum value to the 90% of its maximum value. And during this fall time, the current drops from 90% of its maximum value to the 10% of its maximum value. Simultaneously, the voltage gradually rises to 90% of its maximum value. So after T off time, the switch again regains its blocking properties, and we say the switch is off as there is no current flowing through the switch after this point. So this T off time, or the time to take the switch from on position to off position, is combination of the storage time and the fall time. And we can see that there is again certain switching losses occurring across the switch. So this is certain basics about switches, and we have seen the characteristics of an ideal switch and the switching characteristics. Now we'll go into detail about various power electronic semiconductor devices, which are nothing but switches, in next video lectures in this series. This is all for today. Thank you and have a nice day.